Thanks. Today I'm going to talk about online thinning for high-volume streaming data. So first, this is joint work with Professor Villett at the University of Wisconsin-Madison. So first, let's talk about what is data thinning and what I'm talking about. Let's take a look at an application as an example first. So this application I'm talking about is called VAMI, Wide Area Motion Imagery. Basically, what you have is usually you have an unmanned drone or like that, a balloon flying in the sky, having a camera mounted on it, and it's taking video while it's flying. And it will take the video and try to, at the same time, try to communicate with the ground base to tell the base what's happening in its vision, in its field of vision. So because it's usually wireless communication, there is very limited bandwidth and also limited battery power. So a lot of cases, what they will actually do is they will fly out the drone for a few hours and then fly it back to the base, have someone look at the whole video for a few hours. Then you end up with having a very long delay over what you can see and what's happening in the field. What they want to do instead, is instead of having them fly out and fly back and look at the video, is have some real-time low bandwidth transmission with the drone directly so you can see something happening there. But the problem is, because of the bandwidth and battery constraint, you cannot transmit everything back. You either severely compress the video or you have to select what to transmit back. So that brings us the question of how to do it. So what we propose to do is when we take a look at the field, we try to implement an online saliency detection method, basically find out what looks different in the field that could be a point of interest, and transmit only those patches back. For example, in those, you can see the houses that occur very often, the trees are common, so you won't flag them as important or salient, and you would only transmit like things like people, animals, and perhaps the strange-looking gate to the base. So it becomes a data thinning, so you're just trying to figure out what data is important. So the goal here is discover anomalous objects and occurrences in high-dimensional streaming data. There are a few challenges. First of all, because it's high-dimensional data, the algorithm needs to be scalable. Second, because the drone is flying all the time, you need to adapt to changes in the environment. Like you could be flying over an ocean. The environment is very different when you're flying over a city. So, and the different, like what you consider salient or anomalous would also be different in that scenario. Also, because the drones usually have some vibration on itself, the algorithm is best if it's robust to those moving platforms and vibrations. So there are a lot of existing methods in saliency detection in visual saliency detections. First, we can think about as motion detection. This is good if you have a stationary camera, but the problem is, first of all, it cannot discover stationary anomalies, and also is not really robust to vibrations. The second kind of method is the classical visual saliency detection. So basically look at the field and look at what's visually interesting to people, like edges and corners and high frequency things in the image. So a lot of times those detection methods work like high pass filters, and it detects strong edges and corners. So here is an example, but the problem with this kind of method is if you're in a visually complex scenario like cities, you have a lot of buildings and people, and if you look at, human looks at it, all the buildings may not be salient, but to an algorithm like that, they have so many corners and everything will be flagged. So what we proposed here is a cluster-based method where you first basically divide the image, every frame, into little patches, and we learn a distribution over those patches and group those image patches. Then we will know what is common and what is not. For example, here, all the tree leaves and tree trunks and the roads will be clustered into their own little clusters, and then the person is not well represented by any of those. We can then figure out, oh, this is a low probability occurrence, and we can flag it as our salient patch. So what we use is a Gaussian mixture model here. So each group is a mixture component. And to alleviate the problem brought by high dimensionality, we use a low-rank covariance matrix model. So basically, the covariance matrices here is represented by V as the low-rank representation, and lambda is diagonal. And here, the sigma squared I is basically say, OK, the patches don't have to live exactly on the low-rank space, but it lives close by, and it's more a robust model. So it ends up being like a union of subspaces model, where you have tree trunks in one subspace, roads in a second subspace, and green leaves in the third. And the human doesn't live close to any of the subspaces and can be therefore flagged. The challenges in this model, first of all, if we have changing environment, then we need to track the changes in the subspaces. You can't have a stationary model and just leave it like that. So first of all, you need to track the changes. And then when your field of vision changes, there's also the potential of changing numbers of mixture components. So we need to think of a way of how do you add in new mixture components when you have more complex visual field. And when two components become closer together, how do you merge them and trim them? The main steps to keep it short, basically, we initialize the model, mixture model, with a small number of training samples. Then with each new frame arriving, with each new observation, we compute its negative log likelihood under the current Gaussian mixture model as its anomalousness score. And we update the mixture model parameters using unions of subspaces tracking techniques. Then we basically take a look at how complex our model is and how well we're fitting the data. We either merge or split the components. And we flag whatever observation that comes with a high anomalousness score and transmit to the ground for future analysis. So here I'll show some experiment results. Basically, this blue line, this is the ROC curve. This is synthetic data where we have streaming in 9,000 total data points. 95 of the data lives in two subspaces. Those two subspaces slowly rotate over time. And the blue line is the online thinning algorithm where we use the union of subspaces technique and also have the merge and split with of the mixture model mixture components. And we compare it with two full-rank Gaussian methods. One is just a batch-based Gaussian classic. You get all the data and train a Gaussian mixture model on it. And the other is an online Gaussian. We initialize with the first 1,000 samples and then update the model online. And two other, the MPPCA and MMLE, MMLE-MFA, both are low-rank models. So they use the low-rank covariance matrix, but they're not online. So you can see here the online thinning, because it's both online and uses the low-rank assumptions, it actually outperforms all the other four algorithms. The second, most of the algorithm I've shown before, they cannot determine how many mixture components are there. So ours can determine how many mixture components are there and compute them automatically. So here, the ground truth is we have 4 mixture components in the first section, 2 mixture components in the second section, and 4 in the third. So after each change, this here alpha value is a tuning parameter in our algorithm, basically say how long the history I want to remember. It's between 0 and 1. The larger it is, the longer history it remembers. So we see after each change, the algorithm converges to the correct number of mixture components pretty fast within a few hundreds of samples streaming in. I'll show you some in motion. So this is the a video taken from a camera on a drone. You see it's very shaky. It's basically the field is a parking lot with a car and 2 people coming in and out of the field. And it's pretty clear the anomalous thing would be this car, and the people. All right, let's go to, and with the online thinning method, so the red patches are the patches we flag as anomalous. What you see is even with the vibration, it very consistently flag out the people and the car. And when the other car comes in, it's also flagged. So here you see some false positives here because we select 5, we just say at every frame, pick 5% of the top anomalous patches and send it back. Oops, sorry. So we have a fixed bandwidth. So you will, because there's not so much interesting things in the field, you're going to have some false positives. And we compared it with one of the state-of-the-art visual saliency detection algorithms called the Sun. And here, the 2 upper frames are the originals, and lower here, the green is patches flagged by both algorithms, so successfully detected by both algorithms, theirs and ours. And the red is the Sun algorithm. They flagged alone, we didn't flag it. And the blue are the patches we flagged, they did not flag. So you see, the Sun algorithm missed the people quite a bit, although they flagged the car very well. But also because it's a visual saliency detection, it also flagged quite a bit of the high frequency grass field. So one more feature I wanted to talk about is on a lot of those, we have the vibration we saw severe. So we want eventually stabilization because people don't really like the very shaky videos. So this can be done on the ground. It doesn't have to be done on the board. So with only transmitted patches and a very few reference frames, we can stabilize the video, and it looks something like this. This is I'm running out of time, so I'm going to skip most of these. But one last thing I wanted to mention is, although I've only talked about pretty much one application, the VAMI, this framework is pretty general, and we can use it for different kinds of applications. For example, this is the Enron email database mining. So we applied our method to the email database. This is basically, this database has the corresponding emails within Enron, the company, from 1999 to 2002. And we counted how many, we set a threshold of anomalous score and counted how many anomalous emails there are per day. And we applied a Gaussian filter just to make it a little bit more smooth. And we flagged out the peaks. Basically, you can see the things that are flagged out are the big events happening in the company. For example, CEO changes, big blackouts affecting numerous customers, and another CFO ousts, and the shares plunge below $1, and another CEO change. So basically, this is the online anomaly detection method based on a dynamic low-rank Gaussian mixture model. The algorithm it's robust to high dimensionals problems because it uses a low dimension unit of subspace model. And the online tracking allows adaptation to changing environment. And we are pretty robust to vibration and missing data. The general framework can also be used in various applications. Thank you for your attention. We have a few minutes.